It's just about 3:30 here, just a little ahead of that, so we'll get started here. Couple of things. Welcome to TAB 2019. We're sure glad to have you here. It's great to see so many people here for this presentation. I'm David Osmo. I'm a regional engineering director with the Sinclair Broadcast Group based out of San Antonio. And before we get started, I'd like to thank Sony, the folks over there, for their continuing sponsorship of the engineering conference. Don't forget to thank Mary and the rest of the people at Sony. Just stop by their booth tomorrow at the exhibit hall. And it's now my privilege to introduce our speaker. Brandon Cline is the Senior Engineer and Director of Engineering for BeckTV right here in Texas. His role includes consulting and coordinating with the project team on facility design and extends to overseeing the broadcast system's project management, equipment specification, documentation, on-site supervision, and commissioning. He became the lead engineer on numerous builds, including stadiums, broadcast facilities, corporate AV, operation centers, and Brandon, we are so glad to have you here this year. Brandon.
Thank you, David. Like you said, welcome to TAB. I work for BeckTV, which is headquartered here in Pflugerville, just about 15 minutes north of here. Beck has a lot of experience integrating broadcast facilities for 30 plus years. You probably know Fred Beck. He sort of built that from the ground up. Over the last 8 years or so, 9 years or so, we've been doing stadium work and getting into other markets, house of worship. We've done a lot of trucks, stuff like that. And very recently, this wave of IP technology being part of your infrastructure has been a real question as to when to dive in. And fortunately or unfortunately, we've been on that cutting edge and done a number of installs with this technology over the past 3 years. We've reaped some of the benefits for our clients of what that can do for you, but also have realized a lot of pitfalls in terms of where the gaps are to make something that sounds very robust actually work on the back end and make it usable. And so typically what we do large installs. That's how we're built. We want to do full TV stations. We want to do full stadiums. We dedicate an engineer to a project. We have very good engineers. Our model is that engineer will take that client from start to finish, help them specify, help them choose manufacturers. We try to be agnostic, but give guidance onto, this product does this very well, but it may not do this, and this product does this. So walk them through that, let them interface with the manufacturers, and really give everybody a shot to prove that their product is going to fit into this architecture. So they come to us now over the last 2 years and they're asking, should I go IP? And that's a complicated question. And I think it's one that Beck wants to be the consultant or advisor. Even if you just called us up and asked us a question, we want customers to come and pick our brains about why they should do this or why they shouldn't do this. And I think that you'll be at this show and you'll go see a lot of manufacturers' booth and they'll tell you all about how great their IP technology is. It may not be as honest in terms of what it can't do or where the problems are as what an integrator would see, because we put it in and we see the problems over and over. We also see the benefits of it. So this presentation is basically going to walk you through if you got a big chunk of change and you got a project you want to do in the next year, and you have to make this decision: am I going to go with an IP core? Am I going to go with a switch, a network switch as my spine router to future-proof myself, or should I stick with this technology that has worked exceptionally well for the last couple decades? And we can start with that. So here's a couple facilities that we've done. Some of these are baseband and some of these are IP, and you wouldn't know the difference looking at the control room, and that's kind of the point. Ultimately, the operator is going to expect consistency in his intercom system and his routing system. If he routes something, it should be there, right? That's the expectation on the back end. So they don't really care. For the integrator, it's very different. Our infrastructure is very different. There's a lot more fiber. We're not running all this copper cable and terminating it. We have to figure out how to demarc this fiber in ways that is manageable and can grow as the system grows. There's really four main topics that I'm going to talk about in this, and you'll realize it'll sort of shift heavily towards the IP side of things, because I think that most of us are familiar with SDI and baseband. But it's choosing between the two. What are the benefits? What are the detriments? What are the common pitfalls that you may come across if you're doing IP technology? And then as an integrator, we're very concerned about how this gets installed and how it gets installed in a way that is usable and can future-proof you. And it's very different than a model that we've had for a very long time. We've been very, very efficient in how we've cabled broadcast facilities to this point. Patch panels and routers and switchers is so secondhand nature to us that now we're getting into a place where we're not actually terminating the cables, or we could terminate fiber, but that may take too long, and it may be cheaper to buy a patch cable from a manufacturer, and get it specified to length. I love SDI. I still love it. By and large, if you know what the end goal of your facility is, and it is of a size that you're comfortable with fitting in a 288 or even a 576 squared router, you know that you're not going to grow bigger than that. You know that you may not go 4K. SDI works. It's reliable. It interops as you plug one cable from your router to a destination device, or you have a source that you plug into your router. There's no communication that has to happen between two manufacturers to say, hey, why can't I see your SDI signal? It just works, right? We know that. It's easy to troubleshoot. You have patch panels. You know that something's going wrong. You follow this one cable that's carrying this one signal. You can patch it wherever you think the problem is. You can plug it into your QC station and say, okay, here's what we're seeing, and here's my problem. We can address that very easily. And at this point, it is cost effective. It's more cost effective than IP is what we've seen. That may not be the case in years to come as the cost of switch fabrics decreases and the need for SDI gateway conversion to IP decreases. But at this point, what we're seeing is we're putting a lot of baseband routers around an IP infrastructure, around an IP core. And that doesn't double your cost, but it certainly increases it above what it would cost if you just stayed with an SDI router. I think the biggest concern that clients would have coming to us this year and saying, should I go SDI or should I go IP? When it's clearly a facility that would fit very well with a baseband router, is all they're hearing about is SMPTE 2110. And it's all manufacturers are talking about, and it's all the manufacturers are putting their R&D into right now, especially infrastructure companies. So you know that all of these smart engineers, all these smart people are working on SMPTE 2110. They're not working with the SDI router or the SDI multiviewer that you used to use. So you have a risk of buying technology that, although mature, may not have the back-end support that it used to. And you know that that's not where the development is happening right now. So there's this risk and concern of falling behind, and also a product going end of life. That's a real concern, and we don't know the answer to those questions when we get asked it. I don't know when this this CG is going to go away. But by and large, I think that you're fairly comfortable saying that my router is going to work for a long time. And quite honestly, it'll likely work longer than some of the IP technology that you're going to buy right now, which has a shorter lifespan than what you would expect in the past. With SDI, you're probably looking at 10 to 15 years with IP and how fast switches are changing, and the capacity and the SFPs you can use and the interfaces that different sync devices have. That's changing so quick that maybe you think you're future-proofing yourself, but in some ways you're not. The real benefit or the real detriment to SDI is 4K is tough, right? You cut everything by 4. That's a real benefit of IP, is this huge bandwidth that you get to shoot down your pipes. And then if you got to expand, if you're looking at a very, very large router, or you're looking at tying 2 very large routers together, it's really time to look at IP, because it makes a lot of sense. IP can scale as you scale. That's the real benefit, and you can buy what you need when you need it, and not have to sort of buy a 576 squared router when you just really need 280 ports, So why build IP? Like I said, it's scalable, signal efficiency, getting multiple videos and audios bidirectionally down every fiber that you have, easy to reach to remote areas of a campus or country, really. Flexible distribution. Centralized processing is interesting. I think that what you're going to find right now is that a lot of manufacturers are coming out with products that are doing a lot of different things, kind of Swiss Army knife. If you think about the way frame syncs have been in the past, they're frame syncs, but they're also audio processors or multiviewers or scalers or transcoding, and all they do is you send a fiber straight from your switch into this processing FPGA block, and you decide what it's going to do, what it's going to be that day. Maybe it's going to be a 4K up converter, or maybe it's just going to be an audio shuffler, or whatever you need it to be. That's a pretty cool thing that's happening right now, and really everybody's doing it at some level. The reduced upfront cost, like I said, it is more expensive, but you do just buy what you need at the time. So, an integrator can help you price that out. They can tell you, okay, well, let's model it this way, and if you buy SDI, you're going to have to future-proof this, but if you buy IP, we really just need to buy this right now. So there's a game to be played there. And like I said, it's the current technology. It's what everybody is putting their money into and their smart resources into. And that means something. When you call up a manufacturer and you want to know something, you want to talk to guys that are in the know, and that's where they're putting their efforts in right now. And one last one, which I find interesting, is marketing. Now, not everybody's going to get a marketing value out of going IP, but to this point, you've had to be a little bit of a pioneer to do it, and that can pay off, and that can pay off in different ways that you can monetize. Now, that's not for everybody, but I've certainly seen it, and it's certainly made a difference in why people have chosen this. Why not to build a new IP facility? So this little slide has these 2 guys, and it says, when you put it like that, it makes complete sense. It's very complicated. If any of you have dealt with it, you would understand how complicated it is. And we'll do a job, and it'll be super complicated, and then you'll get a few months down the road, and you're like, maybe it wasn't that complicated, and then you do another one, and you're like, that was really complicated. And part of that is because you can't follow the signal path. It's hard to model it in a drawing. We used to provide as-built drawings to our customers, and you could say, okay, this is how the system works. Now, so much of the system is actually modeled in really a cloud. You don't know what signals are traveling down which fibers or which part of your switchblade that they're running down. You can't patch it out and see it. So you have to be in tune with network technology and really be almost IT savvy in a way to explore what's happening within your system. That gives you a lot of flexibility, but it also gives you a lot of complex workflows. I think that we used a term once, complexability, which is a good way to define it. So it's immature. right? So you may have the big companies making infrastructure, and they're making a lot of parts and pieces to make their system work. But there's not a lot of the end devices. They're just starting to come out. And so you're missing a lot of these pieces that make the whole puzzle work together. And the other problem with that is, even if there is a piece that may fit your need, it may not talk and communicate back to your central management system. Poor interoperability, just that, you know. I mean, when we get NMOS to a point that we feel comfortable, I'll let you know, but I can guarantee you right now it is not there yet. Hard to troubleshoot, you can't patch. This is one that we see as integrators is, not only is this new for us, this is new for manufacturers, and it's new for clients. So we can build you a system, it can be stable, it can work, and we can try to hand it off. And you may not have an engineer that has any experience in how to troubleshoot this. They are very familiar with troubleshooting a classic broadcast design. That's been a real bridge. That's been a real challenge for us to hand off a system where, you know, the client has made this decision but didn't really back it up with the talent needed to support it after we leave. A difficult buying cycle is another one. If you're going to put in an SDI system, you would say, okay, well, this graphic system I really like. It's been around for a long time. This switcher works really well. This router works really well. Let's go with what we know and what's tried and true. With IP, you say, okay, well, I'm going to put in this infrastructure, but I know that that company's got a product coming out in 3 months or 6 months that's really going to fit well. And so then you bank on products that haven't been deployed, haven't been tested. You know, the software is going to be immature. And you're going to go through a science project. And you're willing to do it because the risk of adding it to your system is going to give you a benefit that you can clearly see. And that may be not going through a gateway. It may be a reduced price and being able to distribute things to the edge without these centralized gateways or different things like that. And that goes to the, you know, new products goes right into sort of firmware updates. We've spent a lot of time on site commissioning, and our commissioning time has almost quadrupled installing these projects because there needs to be development, and there needs to be development because a lot of these things that you're doing, every project's a little different. As much as it may look like it's the same thing, every project's a little bit unique, and a manufacturer is going to see something that they didn't expect, and they have to address it for you, and for the client and for us. And we make sure that that happens, but it certainly costs time. And hidden costs, I'll say this, you know, our installs have typically been CapEx money, right? You say, here's $5 million. Let's go build a facility. And what you're seeing now is kind of the trend of really our world right now, which is there's so much OpEx money that goes into support and warranty and services, especially for monitoring your systems and different things like that, that it's a new model that's being approached right now in terms of supporting a system like this, because it's not a wire it up and let it run. It needs maintenance. It's needs more maintenance than any facility that I've seen yet. So I gave this talk before, and somebody had mentioned, what about hybrid? This talk is really based on, if you get a new job, a big new job, what do you do? I think that if you have an existing facility and you're looking to dabble in IP and what it can do for you, there's certainly ways to do a hybrid. And in fact, it may be smart. There's a lot of router cards that can that are baseband internal, but will provide you IP on the surface, and then you can start to support different edge devices that are IP based. And then ultimately, maybe you want to do this forklift and switch over to IP. I think that's okay, and I think in some models it works really well. At this point, you know, I think that you're going to get a little bit of hybrid no matter what you do. And really, if you're putting in an IP system, it's hybrid already. Now, it may be IP centric, but you have so much SDI and so much legacy gear that you're really not getting away from a hybrid system. But if you have an SDI core, you can start to play with adding pieces that eventually you think you may make that move to IP later. The last time I did this talk, I really did the same thing where I kind of talked about everything before I actually got to the slide that I actually talk about it. But this goes a little bit more in depth, and it talks about this scalability idea. And you're going to buy this big switchblade in IP. We'll call it a spine. You've probably heard that. You get this spine and you get these 100 gig QSFP ports or 40 gig QSFP ports. And if you have remote locations, remote control rooms, you bridge more network leaf switches out to those locations. If you have to upgrade your spine, you can take your spine and make it a leaf. So if you architect this the correct way, you can continue to grow and reuse the product that you've already bought. That's an advantage in the sense that if you need a new router and it's SDI, that's a forklift. If you need to add capacity in IP, you really get to reuse the stuff that you've already purchased. And that can continue to grow, but you need to be very careful in how you do it. And part of that goes into PTP, which I'll talk about in a little bit. But the architecture of your switch and your media over IP networking is very, very critical because PTP is this reference that's pulsed through the system, and it's got to be dealt with very intelligently and carefully, or else you bring everything down. You know, if you've ever turned off your sync generator in your facility, you know that's not a good thing. It's basically the same thing that would happen if you do it the wrong way. Efficiency, like I said, you can get 10, 25, 40, 100 gig pathways. And those can all be on 2 fibers. Now, 40 and 100 typically would be on 8 fibers, but you can get the SFPs that'll do CWDM. So you can start extending 100 gig out to a remote location if you have limited bandwidth or limited quantity of fiber, dark fiber that connects 2 places. 100 gigs is a lot. And depending on how you're running it, you know, you get, 33 signals of 3G, double that of HD. So, that's not even considering if you start to compress stuff. They're also agnostic. Switches are agnostic, so your capacity is really based on what you're trying to move around. And we're moving around all sorts of stuff now. REMI productions is a real big thing in our world, and we have to figure out how to transport low latency compressed signals across the country. And you can send them right into a switch. It can be MPEG-2, H.264, HEVC. It can be something like LLVC. It doesn't matter. Your switch is just going to pass it because it's a multicast address. Scalability and efficiency obviously goes right into 4K. Being able to carry all your signals on one fiber duplex is a nice way to work. I mentioned 12G SDI, which I'm not really going to get into here. I think that there's a place for it, but if it doesn't pick up, it doesn't really matter. This is really what people are focused on right now. You don't have to have your large iron central router. This is a spine and leaf model. We still put in quite a bit of spine and not as much leaf, although typically you would have 1 or 2. And the reason for that is your central spine usually has enough ports to support most installs. I would say if you put a chassis blade system in, you could support almost any 95, 98% of installs that are out there right now. So we talked about this. The cost-effective nature of IP is this idea that the ubiquity of network switches is going to bring the cost down of buying those switches. I think that when I was talking to one of our engineers, you hear the word COTS a lot, this off-the-shelf, consumer off-the-shelf switch, but really these are not off the shelf. These are special switches. These are not what you're putting in to run most of your corporate network. These are dedicated to very, very high bandwidth media streams or backbone for very, very large corporations. So it's not there yet, but maybe it gets there for us. We talked about processing, and this goes to this cost, these ongoing costs that may be hidden, and that's licensing of different features of a switchblade, or I shouldn't say switchblade, Swiss Army knife processing block. But it's valuable. You can do a lot of different things, and it's flexible, and you can determine what a processor is going to do. You hear about microservices, and really what it's happening is it's flashing FPGAs and putting on the new code that you need to run whatever you need to run. And these are just some of the things that they can do. I think that one of the ones that we're really eager to see deployed more is in multiviewers. You know, the real bottleneck with multiviewers in the past has been this: everything has to be discrete to each multiviewer. That takes a lot of ports. It makes cross-point cards very big, and you're just regenerating that signal over and over and over to each multiviewer. In this world, we have a network switch with multicast addresses, so it makes sense that we only make one copy of a source. We scale it. It's a lower bandwidth, but it's reusable, and then multiviewers can just subscribe to this. And we're seeing different companies start to come out with different models of doing this, but instead of having 36 direct lines to your multiviewer, you just have a pool of resources. It can give you higher density on your monitor wall, and it can look very, very good as well. So it's our job to sort of educate our customers and let them know where we're seeing the biggest problems. So I don't know what I put in here. Let's see. Oh, I'm sorry. I just can't keep up with which version of the truth you're giving today. I don't believe that one either. So we get told a lot of things, and clients get told a lot of things, and quite honestly, manufacturers believe a lot of things that they're selling you. The reality is there's specialists that are making these products, that are writing the code for the product and are telling you what it's capable of, and then when it actually gets deployed, it may not be exactly what you were told. And that's any cycle, but that's the cycle of a product that's not mature. These are serial number one. We've put in so many brand new products over the last 3 years. It's hard to get away from the fact that they're just not ready, and people are eager for them. So they get pushed, and manufacturers get pushed to get it out because you're like, I really need this, I really need this, I really need this. It's coming. And they get it to you, and you realize you have 4 months of working out bugs and getting new code and figuring out all the problems that they didn't know because they couldn't simulate it in a lab. You cannot simulate, a 30 antenna intercom system, in a room. You have to put it out in the field, and you got to put it out in the field when there's a stadium full of people in there, and that's just an example, but it goes on, right? Interoperability, ISO 4, ISO 5, it's coming, it's not there. I would say that one of the things that we've started guardrailing ourselves for is in these systems almost expecting interoperability not to work. And that means our control systems not necessarily talking to this endpoint device. That's the way it's supposed to work. Control system goes to the endpoint device, says subscribe to this multicast. That device goes back to the switch and says, okay, release that multicast to me. I'll make the switch. Well, if they're not talking the same protocol, that doesn't work. And that means drivers have to be written on the control system side, and that the sync device side has to have written their protocol correctly. and that's not always the case. So one of the things we've started looking at is using natting, network addressing tables, so that we put a device in between our switch and that end device, and we can control this NAT, and all it's doing is generating a multicast stream that is constant for that end device, so it's never asking for anything. We're just changing the multicast right at this one spot. Soon that's going to be able to happen in a switch. We're already hearing rumors of it, and it's going to be very nice. But it can also just happen on an SFP. So that's fairly cost effective, and if you model your system with enough ports and enough contingency to take care of that, you can just add some SFPs into your switch. You don't even have to plug a cable into them. They can do a NAT for you, and you can control every end device in your system to make sure everything gets a valid signal. The complexity is not something integrators can help you with. It's something that you're going to have to make a decision on when you pick a manufacturer to support you afterwards. You're going to get a lot of information. You're not going to be able to process it all at once. You're going to need to go back to them and say, can you go over that again? Also, this isn't working. Can you tell me why that's not working? They'll maybe make it work or come up with a workaround. But it has to be a relationship that you feel comfortable with and you can grow with. And that includes your integrator. You got to feel like you can go back to your integrator and say, why did you do this? Why did you build it this way? And you got to continue that educational process, which is much more involved than it used to be. Mixed endpoints. I don't know if that's a pitfall anymore, but you still have a lot of SDI in your plant, and how you're gonna deploy your gateways from SDI to IP is still a conversation we have internally. I still like to put patch panels together, and I put all my gateways in the same spot, and it basically gives you an SDI router. If you start to deploy them out to all of your racks, well, now it's a lot of extra cabling to have a centralized patch location, which doesn't make a ton of sense. Also, you have ports that are spread out all over your room, and you lose efficiency in what those ports can do for you. You know, you want to be able to add the next thing in your router. You don't want to have to say, well, that gateway was dedicated to my clip playback, but now I ran out of spots over here for my scan converters. I'll just repurpose a port over there, and it starts to get very confusing. But ultimately, I think top of rack is probably the way things are going to go, and you're not going to run through patch panels. You're going to have little devices, little pucks that you just say, give me an SDI, give me fiber straight into my switch, and that's it. A little bit the way, analog to digital happens. Audio manipulation and PTP have their own section. Those are probably the biggest things that we're seeing that cause us headaches. We've talked about all these. Reliability is sort of an unknown. It's about the reliability of what a switch company can tell you their switch is going to be. But also the switch companies are replacing switches fairly quickly. So you may have a reliable switch fabric that is not being sold or supported anymore. And so you have to get into this scenario where, well, maybe have to trade up or buy the new blade or trust that this is going to work for a long time. The other part about reliability is SMPTE 2110 is designed for redundancy, right? All these source devices and end devices have two NICs, 2 ports, and you can split them to 2 separate switch fabrics, to 2 separate routers. We don't really know the cost benefit of that yet. We can put them in, and it basically doubles the cost of your system and gives you great redundancy, and it works fairly well. But we don't know that that's actually giving you the monetary value that you want out of it. That could be 6 cameras. That could be all these other things that could make your production so much better, when the fact of the matter is that these switches may be very, very reliable and they may not go down. But you have to make that decision for yourself, and it kind of depends on what type of facility you're running. If you're running a sports stadium where you have a lot of downtime and you can do maintenance, not having a redundant switch fabric may make sense. If you're running a network news, a national network where you can't have that risk, well, then maybe you look at it a little bit differently. Or maybe you model it with different levels of redundancy and say, I'm going to make a smaller switch fabric for my important signals. And IP probes is another thing that we really need as engineers to troubleshoot and commission. We don't have this patch panel anymore. We don't have this waveform. There are waveforms that take SMPTE 2110, but you have to route to it. You're not intercepting a signal. You're not monitoring what's happening with the telemetry coming off of your switch. And some of these products exist right now, but it's hard to convince the customer it's worth the money because it's expensive, but it's the only thing that gives you insight. And so now we're getting jobs that may come from a consultant and they have all the parts and pieces to put a system together, but they didn't tell the client that you may want this thing that helps you look into your system and QC and troubleshoot it. And it's our job to sort of push that and say, hey, these are the things that we really need to look at if you want to be able to control your system and know what's going on. Addressing the IP pitfalls, continuing here, and the big one I talked about earlier is I think that there's a gap that opened for a new type of engineer. We always used to be broadcast engineers and IT people, IT guys, and we would cross over where we had to, but the broadcast guys were like, just give me a bunch of 48 port switches, I'm going to make a bunch of islands, and then you can trunk it over and we can get this pathway to the internet if we need to, or we put a couple things on the DMZ and you just explain what you needed back and forth. You cannot do that now. You need somebody that knows how to program a switch, what's happening on a switch, how to use Wireshark. And I call this the purple squirrel. That's what we're looking for at our company when we're hiring engineers. We're looking for somebody that we can train that's from IT and train them how broadcasting works, because IT people have no idea how broadcasting works. And broadcast people typically don't have maybe just the dangerous enough of information to mess with a switch. And so it's very hard to teach broadcasters to be IT people because you're not touching switches every day. But that's what's going to happen, where we're going to touch switches every day. We need our clients to have these purple squirrels so that when we hand off systems, we're comfortable with them being able to take it over. And manufacturers need these purple squirrels also because it's just new. It's where we're at right now. Lots of mouse clicks, lots of multicast addresses, lots and lots. If you think about one signal, you have your video, you can break out your audio into 16 different multicast streams. You have metadata. You have all sorts of multicast that can float around in the system that can get into hundreds of thousands, and it's hard to keep track of all that. I'll just jump on the audio problem real quick. Audio is carried in the multicast, and it can be multiple audios in one multicast, in one flow. It can be stereo. It could be 4 audios. It could be 8 audios. I think that they actually even go up to 64 in certain scenarios if you're trying to do a MADI type stream. The real problem with that is you basically don't have a mono router anymore unless you make it all mono, which has very big inefficiency problems. Most end devices only have a few receivers, so if you make all of your audio on every signal coming in mono, that's 16 channels, and you route that to a device that only has 2 receivers, you only get stereo. If you need all 16 channels, if you're recording on a replay system, they may only have 4 receivers. You need 16 channels, and you need to be able to shuffle what those 16 channels are. That's a real problem because now we have to have 4 audios within every flow. But we can't break up those flows, not within our switch. So we have to send it externally to another system that can do that. And we've been using audio mixers to help us with that because they natively have been doing this for quite a while. And so they can take those streams and break them up, repackage them, and send them back. The other thing you can do is you can put aggregators, basically frame syncs in front of these devices that may need 16 channels and need shuffling, and you have to sort of manually go through and do it. But mono shuffling in this world is difficult, and that primarily falls on sports installations that do a lot of mono listening, a lot of demux and muxing at record devices and for operators with Wohlers and stuff in front of them. So that's a real problem where we need this external audio router because we're mapping our systems with 4 or 8 flows is fairly typical. And if you got to get AES67 to a mixer that's not natively AES67, you usually have some sort of converter in between, and that's only going to have so many receivers. So you want to maximize how many audio flows you actually have in those streams so you can distribute more cost effectively and cleaner. Ultimately, I mentioned this here, if this can become a little bit more like Dante, that would be great, right? Dante has 4 audios in each one of its flows, but to you, it looks like a mono. You go to Dante Controller, you select it, and you don't know how many receivers exist in that end device, but it lets you take the flow and pick the stream that you want out of it. AES67 is not working like that right now. It doesn't let you look at it. Like if you deliver a stream, the receiver is just going to take whatever payload and whatever order it comes in. So ultimately, if we can make end devices go and say, give me this stream and I want channel 3 for this one, and give me this stream and I want channel 6 for this map to channel 2 of this receiver, that's going to work great, but that's really not where it is yet. PTP is the other big one, right? This is your reference. I could give a whole talk on PTP, and I still don't know what I'm talking about. So I've seen PTP be problematic basically in every job we've done so far that required it. The model's sort of simple, which is you have a couple grandmasters, just like you have now with sync generators. They feed into boundary clock switches. Highly suggest having boundary clock switches and having a good boundary clock. The boundary clock will protect your masters and become the master for all the slaves below it. So it minimizes traffic. It minimizes traffic across a layer 2 and just distributes PTP to the ports that need it. It protects your system from, if you added another device that wants to be a master, it'll say, no, I'm told that these are the only 2 ports that can be my master, so you can't flood my network with other crap. And if you had a real problem and you lost your generators, your clock can take over, your switch can take over and be a clock. If you don't use a boundary clock, you don't get any of those advantages. So typically you take these into 2 separate boundary clocks, and that's for redundancy purposes, and then you distribute out to your leafs, or if you have just a big spine, you would land it on 2 separate spines, spine blades, and distribute it out, and just make sure that the architecture is done correctly so that you're stable. And what we're seeing is it's not necessarily a problem for just your video, but typically what we have is we have this spine, and then we have all these 1 gig switches that are doing audio mixer or doing AES67 intercom or various other AES67 architectures that need PTP. And they may need PTP to be tweaked a little bit for them. And they may, you may have an architecture, in our case, where we just had 2 different switch manufacturers and realized that was a real problem going from one switch manufacturer to another switch manufacturer. So this is certainly something to think about, and you really want to save money and say, well, we can, it's not, how important is it? It's real important. So this is not a place that you would really want to cut your costs on. You want to make sure that this is your heartbeat. You know, you lose timing, you lose everything. I talked about COTS being knots, you know, not off the shelf. Boundary clock, transparent clock switches, PTP, SMPTE 2059 is sort of the future for what our reference looks like. Yet we still have to run a lot of blackburst to gear, and we're not really sure why. But but I think it's because historically broadcast gear was just happy having black bursts. So we do it as sort of a backup in some of our designs. The other thing is, the last thing I'm going to talk about is fiber infrastructure. So this impacts us quite a bit, and as integrators, as installers, and it's actually kind of fun. It's remaking our model. Our infrastructure now is becoming, especially in the SMPTE 2110 projects, primarily fiber. And we have a lot of fiber that comes in from the outside, and then we have this big fiber infrastructure that happens on the inside, and you want to decide how to patch effectively devices to your router. You port rep your router out like you would do for a SDI to a patch panel. You don't want a whole lot of people, messing around on the back of your active routing switch. You got to choose whether you want to use single mode or multi-mode. You could use MTP cables that are MPO 12 or MPO 24, and they can carry a whole bunch of signals for you without having to run a bunch of patches. You get sort of efficiency by these bundled cables. But if you've done it before, you'll see that polarity can get real tricky. And all these devices are typically duplex LC at the end. And depending on how many tub ties you run through, ultimately you could get out of polarity, and you have to be aware of that. Now, there's different patch cables that are designed now where you can just rotate the end. That's pretty cool. The ones that I've had to do, I had to get my fingernail in there and pop a clip out and rotate them, and I couldn't remember which side was which, or plug it back in ultimately. But you don't want to design a system that's ultimately all backwards, which is not impossible to do. And MTP cables, I really like them, but they're complicated to keep straight too. There's 3 different versions. There's a straight through, there's a roll, and there's a paired roll. And there's cassettes that do different things. There's the MPO 12s, which can really carry 6 duplex fibers. But if you're using it on a switch is really, you're plugging in a MTP cable into a QSFP, you're really only using 8 fibers. And that's networking. And they pair differently than other systems. Other systems would pair 1 and 2 together. Network switches pair 1 and 12 together. So all these things need to be thought through. Our customers do not care. We care, because if we don't do it right, it's going to be a problem, and then we have to educate them why we did that ultimately. Other options is AOC cables, active optical cables, and twin acts. And we look at all these for every job because there's huge cost savings based on what you choose, but you could also get into the problem of having too much mix and match, right? If you go everything single mode fiber, you have consistency across everything you're doing. Whereas if you say, I'm gonna go single mode here and multi-mode, I'm gonna use some AOCs and some twin acts, well, now you've kind of created as an integrator, that would be not a system I would want to hand off. That would be a system that you had to make something happen and it grew naturally. But there are scenarios that it can work and it can save money. Obviously, there's a whole bunch of SFP types that you got to be aware of. This is what an MTP cable looks like if you've never seen it. They come in a bunch of different models, and recently I had bought a bunch of MTP cables and bought some cassettes, and the cassettes came out, and MTP is angle polished, so they're angled fibers. And the cassette had a different angle than the cable that I had, which was a little frustrating. So in conclusion, I think there are a lot of reasons still to go baseband. And I think that if you came to any integrator at this point and they were honest with you and you told them what you were trying to do, and for more than half the jobs we do, we get the budget of what you're trying to do. It helps us quite a bit to engineer it to what is actually going to work for you. Whereas if you say, I want to do 4 control rooms and I want to do all IP, but you can't know my budget, we're going to put together an entire package and you're going to be $3 million over budget. So if you work with an integrator, you work with somebody who has experienced this, and you have clearly what your end goals are, what workflows you're trying to accomplish, what your operators expect to see, and what you need to do that for, you can really dial into whether SDI is the right choice. If you're like, we have the very ambitious project, it's very big, we want to go IP, let's price this out and see what it does. What is the products that you're seeing on the edge that can help what we're trying to do? We want to do 4K. There's some real reasons to go IP, and it's getting better, and it's going to get better every year forever, it seems like right now, but who knows? One of the biggest problems that I think 2110 has is it is still uncompressed video, and that means you still have to have a bunch of iron. You still have to have a bunch of products in the way to process your signal. It can't be run through a software stack. There's a lot of different protocols that were designed where you could just send it into a giant software stack and you could do whatever you want, and maybe you got some latency, but you could deal with that. This is not that technology, and so good for us as integrators. Still means you need quite a bit of equipment. So anyways, I would just say, ask an integrator, ask Beck. And that's all I got. I guess I can take questions if there's any time left. I don't know, David. And this guy right here, my daughter always packs that little doll when I travel, and I always take pictures of it doing my installs. So it's more, right? We typically would run a switch stack, depending on how big it is, on a couple 208s. But we've done some that required 6 208s in that one rack, and we'll put out probably more than 10 kW in a rack. So, you compare that to SDI, it's a lot more. And not only that, you're looking at multiviewers, you're looking at these processors that are just doing a lot more. But it may not take up as much of a footprint in your room. So you'll probably have an area that's creating a lot more heat and drawing a lot more power, but it's not necessarily throughout the whole system. But yeah, your main spine can easily get up to over 10 kW. You probably want to try to aim for about 5 if you can, and distribute them across racks.
Is that mindful of like the per channel usage too? I know you talked about rack space, but are you also thinking if I had those modular switches, I had 4 100 gig blades fully loaded up, and I broke it down into 3G channels, how's my consumption per channel of 3G?
I don't know. I think that's hard to know. For us, we have to specify power and cooling ahead of the final design, typically. And so we have to assume that those switches are running at max capacity. So you may design it for a fully loaded, spine switch, but ultimately you may half load it. And you got to be able to tell the GC ahead of time that says, hey, I'm going to specify for this, but when we turn it on, we're probably only going to run at about 50% of that, And if you do have a more distributed, like you said, the self-contained 1RU switches, spreading them out across a couple racks couldn't hurt. But you want to do it in a way that makes sense for your fiber infrastructure, right? I mean, I talked a little bit about fiber, but now we're running fiber pathways above every rack. And maybe it's 2 cable trays. Maybe it's a copper cable tray and a fiber runner, we'll call it. Or we try to put copper below an access floor if we can. But keeping them separate is almost essential now. I mean, I think in the past you used to run a Smurf tube with some fibers in it if you needed to go somewhere, and that was a pain, and it's really not what we want to do. So if you got a couple racks, if we got a router rack or a couple racks that have a bunch of equipment that are heavily fiber-based, we'd probably use IT racks, so you get a little extra space on the side, or put a runner in between, something like that. So you can start to spread them out, but you need to make sure that the design of your room is going to support it as well. That's it. Thank you guys. I appreciate it.